I have a problem. Some time ago, a rock slide blocked off access to the apple orchard that supplies most of my food. I was able to ration my remaining apples to ensure I wouldn't starve, and clearing the path is going better than I expected it to. But while I was figuring out how to ration my apples, I came across the idea of division. See, even longer ago, I woke up to realize that I had forgotten all of mathematics, and could no longer square an integer, let alone a circle. Since then, I've been working to try and rebuild my mathematics knowledge from scratch. I made a lot of progress in my attempts to define the process of division as a means of splitting numbers evenly into smaller parts. I refined my manual process for finding out what some number divided by another number should be, and realized that dividing some number a by some number b actually gives two different numbers as its answer. What I'm calling a quotient, representing how many parts I'm splitting a into, and a remainder, representing a number left over after splitting up the first number. I also came up with a hypothetical definition for division, similarly to how I've done in the past for addition and multiplication. What I still have left to do, however, is to prove that this definition actually works as a model for the process I've described. To start with, let's go over the process one more time. To find what some number a divided by some number b is, I take a apples, and to start with, 0 boxes. While I have b apples or more, I take a box and put b apples into it. Eventually, I'll no longer have b or more apples. At this point, the number of boxes I have is the quotient of a divided by b, and the number of apples I have left over is the remainder. This is much simpler than my original process for dividing two numbers, but still much more complicated than my processes for addition and multiplication. Let's break this down, looking at how many apples are in various places at each step of the process. At first, there are A apples that I have just in a big pile, I guess, and nothing else. If A is less than B, I'm already done, and so the quotient is 0 and the remainder is A. Otherwise, I take B apples from my pile and put them into a box. Now I have B apples in the box, but how many apples do I have in the pile? If I had a specific number of apples in the pile, I could just count how many apples I had. But now that I'm working without specific numbers, it's occurring to me that I don't actually know. Maybe part of the reason division is so complicated is that I missed a step somewhere, and there's some other tool I could be using that would make it simpler. Let's put division to the side for now and consider just this. I have A apples in a box, and take B apples from that box and put them into another box. Of course, B can't be a number that's more than A. To find out how many apples I have left in the first box, all I can think of to do is to consider what happens when I take the apples away one at a time. If I take away one apple, well, if I were to put it back, then I'd have A apples again, so the number of apples in the box would have to be the number before A. After I take away another apple, I have the number before A in the first box, and 2 apples in the other box. And after I've repeated this exactly b times, I'll have some number of apples in the first box, the number I'm looking for, and b apples in the other box. The number I'm looking for is the one that I get if I go to the number before a b times. This seems like a pretty well-defined thing to think about, but it's a bit awkward to describe using the words I have right now. I think I should think of this as another process I can apply, like addition or division. I'm finding the number I get if I take away b apples from a apples. I'll call this subtraction. I'll say that the result I get is the difference of a and b, and that I can write it out as a minus b. Based on what I've already done, I can define it like this. If a is the same as b, then taking b away from a, that is, taking a away from a, leaves nothing. So a minus a is 0. Otherwise, if a is more than b, and c is the number after b, then a minus b is the number after a minus c. So now I have a nice set of two rules that works to define subtraction. That said, it's not quite all clean and simple. Like addition and multiplication, subtraction takes two numbers in and gives one number out. But like division, it cares about the order that the two numbers are in. 5 minus 3 is 2, but 3 minus 5 doesn't exist. I don't know how to feel about an operation that seems useful, but doesn't work for some combinations of numbers. I don't really want to deal with that potential problem right now. As a short-term fix, if it comes up, I'll just say that 3 minus 5, or any number minus a larger number, is just the same thing as with the numbers swapped. There's also something connecting subtraction and addition, in a fairly obvious way, in that when I subtract a number from another number, I'm taking away from it, while adding a number to another number, well, adds to it. 4 plus 2 is 6, and then 6 minus 2 is 4 again. This is similar to something I noticed regarding multiplication and division, which mirror each other in a similar way. If 4 times 2 is 8, then 8 divided by 2 is 4, with remainder 0. Before looking too much into this, though, let's get back to the main task of the day, figuring out if my definition for division works with the process I've come up with. Now that I have subtraction, I can rewrite my process for division to be a little simpler. Each time I take B apples from the box of A apples, I'm subtracting B from the number of apples in the box. Therefore, I can say that the quotient, the number of boxes of B apples that I have at the end, is the number of times I can subtract B from A. The remainder, the number of apples left over, is the number I get after subtracting B from A that many times. As for the definition, it initially looked like this. As with all the other definitions, this one works by first having a rule that describes what happens if one of the numbers, A in this case, is 0, and then another rule that lets me figure out what A divided by B is if I know what the number before A divided by B is. As a reminder as to why this works, since I can always work my way back to 0 by continuously checking the numbers that come before each number, this defines what the answer is for any number. But now that I'm incorporating addition and subtraction, there's a technique that I can use to look at this in a slightly different way. What if, instead of looking at the number that's before A, I looked at the number that's B before A, or rather, A minus B? Here's a concrete example. Let's say B is 2. Let's say that I know what the remainder and quotient are of A minus 2 divided by 2. From my definition, I can use this to find out the remainder and quotient of A minus 1 divided by 2, and in turn use that to find out the remainder and quotient of A divided by 2. If A minus 2 divided by 2 has a remainder of 0, then A minus 1 divided by 2 would have remainder 1, and a quotient that's the same as A minus 2 divided by 2, and A divided by 2 would have remainder 0 again, and quotient 1 more than A minus 2 divided by 2. Otherwise, if A minus 2 divided by 2 has remainder 1, then A minus 1 divided by 2 would have remainder 0, and quotient 1 after A minus 2 divided by 2, and A divided by 2 would have remainder 1 again, and quotient also 1 more than A minus 2 divided by 2. Either way, A has the same remainder as A minus 2 when divided by 2, and a quotient that's 1 more than the quotient of A minus 2 when divided by 2. This simplicity does come at a cost. I can find A divided by 2 for any number if I go back one number at a time to 0, but if I'm going back two numbers, sometimes I can't get back to 0. I have to add another rule for this case, and say that 1 divided by 2 is 0 with a remainder of 1. I'm pretty sure that this pattern should work more generally, and that for any numbers A and B, I can say that A divided by B is 0 with the remainder A if A is less than B, and otherwise has the same remainder as A minus B divided by B, and quotient 1 more than A minus B divided by B. But proving that this works for all numbers, it seems like it's going to be pretty tricky. I think I'm going to have to prove a lot of small things about division in order to prove this, And in fact, I just realized I relied on something earlier that I haven't actually proven yet. I didn't say it directly, but my earlier example for a divided by 2 relied on it being the case that the only numbers that can be the remainder of a number divided by 2 are 1 and 0. It seems obvious that this should be true, looking at how the process for division works, but I haven't actually proven this from the definition itself, which is the whole point of what I'm trying to do now. Let's try and get this out of the way quickly. Based on my definition, the remainder of a divided by b is always going to be either the number after the remainder of a minus 1 divided by b, or 0, if the remainder of a minus 1 divided by b was the number before b. So what would have to happen for the remainder of a divided by b to not be less than b? Well, it can't fall into this category. The only number for which the number after it is b is the number before b. And obviously it can't fall into this one, because the remainder just has to be 0. The only number this rule doesn't apply to is 0 itself, for which the remainder is 0 by definition. So the remainder can never be equal to b. What about a number more than b? I don't think I can use the same trick here. If the remainder of a divided by b were more than b, there's nothing stopping the remainder of a minus 1 divided by b from also being more than b. Although, since eventually, by going backwards, you would have to get to 0, there has to be some number that's the smallest number that has a remainder more than b when divided by b. Let's bring back an old favorite and call this hypothetical number squunge. Since squunge is the smallest number that has a remainder more than b when divided by b, squunge minus 1 has a remainder less than b. And now I can do what I did before. If the remainder of squunge minus 1 divided by b is the number before b, then the remainder of squunge divided by b would have to be 0, and otherwise, it would have to be 1 more than a number that's less than b minus 1, so it can't be more than b minus 1 itself. Once again, this means squunge can't actually exist after all, and so in fact, any number divided by b has to have a remainder that's less than b. That fills in the gap in my earlier proof, and I could try to use that to show now that my definition correctly models my process when dividing by 2, but I would still have a lot of work to do to show that it works for all numbers. Or actually, do I? I'm sort of doing the same thing with my definition here that I'd been doing when I made my process simpler, but it seems like for the definition it's having the opposite effect. It's a lot simpler to state the new definition, but it seems like it's going to be a lot harder to prove things with it. What if I go back to my original definition, and my old process, putting apples into boxes one at a time? If I have 0 apples, I put no apples into B boxes, and end up with no apples left over. So the first part of the definition works just fine, unsurprisingly. And as for the second part, well, with the old process, there's nothing stopping me from adding an extra apple at the end of it. It doesn't actually affect anything that would have happened before. Doing this, if the remainder of a minus 1 divided by b is anything less than b minus 1, I can just see that I get the same quotient and a remainder that's 1 more than the previous remainder. If the old remainder is b minus 1, well, now I can put another apple into each box, increasing the quotient by 1, and leaving me with a remainder of 0. That turned out to be unexpectedly simple. I had thought that having a big complicated process for division would make it harder to prove things about it, but that doesn't seem to be what's happened. Trying to simplify the definition just resulted in making a lot more work for myself. I guess this just goes to show you can't always tell how hard or easy something is going to be until you've jumped in and tried it. That said, I don't think the time I spent on what turned out to be the harder path was wasted. The changes to the process that I came up with make it a lot easier to use in practice, even if it's not easier to prove things about. And trying to make changes to the definition led me to subtraction, and made me think about and prove things that might not have been necessary to prove that my definition works, but could easily be useful in the future. I am running out of time for today, And while I did ultimately accomplish what I set out to do, I do feel a bit disappointed. Division has turned out to be surprisingly complicated, though maybe not quite as complicated as I almost made it out to be. And more than that, it takes a very long time to talk about compared to addition and multiplication, or subtraction for that matter. Maybe rather than talk through all the details, I should start putting together a document to keep track of my progress, where I can write out the details of the wordier and more complicated proofs without taking up so much time. Either way, though, progress is progress. I can now confidently add division and subtraction to my mathematical toolkit, and continue my work.